Okay, this is 7th grade, second semester, Unit 6, Lesson 4. Here's our warm-up activity. Vocabulary review. Describe multiplying fractions using the terms denominator and numerator. Tata.
Multiply the first numerator over the denominator to the other one to get a different denominator for the bottom.
I think I understand what you're trying to say. Can somebody help her out? Help her express herself a little bit with more precision. Jaden.
To multiply fractions, you have to multiply the numerator by the denominator by the numerator.
Very good. So to multiply fractions, you multiply both numerators. You find the product. That's your new numerator. And then you multiply your denominators. You find the product of your denominators. That's your new denominator. So this is how the book says it. Okay? To multiply fractions, multiply the numerators and multiply the denominators. So let's go ahead and do that. Oops, that's not what I wanted. Those together. Here we go. Okay, and then okay, who's got number 1 for me? Or number 2, excuse me. Number 2. Joel in the back, yes. Okay, so when you multiply the two numerators, Joel, what did you get for the numerator? Shh. Joel, what did you get for the numerator? I called on Joel, so you shouldn't be speaking right now. Joel, go ahead.
16.
Which is 16? For the denominator, right? So you multiply your two denominators, and you got 16. What about the rest of it?
9 for the numerator.
Very good, 9 for the numerator. Can you simplify this? No. How many of you guys got this? Good. How many of you guys forgot, but now you're like, okay, this is easy. I remember now. Nobody wants to admit it? Okay. Is this pretty easy? Okay. Who can tell me their answer for number 3? Michaela, why don't you go ahead?
6/25.
Very good. 6/25. Okay. Is that simplest form? Yes, it is. Who's got number 4 for me? Chin, go ahead. 1/20. Very good. Okay. And who's got number 5? Jakari. 6 over what? Very good. 6/49. Let's see here. Here are the solutions. Okay. And then, all right, so we're doing something new today, but you're going to need to know what we covered. I have to say I had the highest number of 100% for the multiple choice so far this year for the last quiz that we took on Friday. Some of you guys will be taking that makeup today. So let's get through this. It's a short lesson like before. What you'll learn to find the probability of independent and dependent events. Okay, and our new vocabulary is compound event, independent events, dependent events. Why learn this? You can find the probability of more than one event, such as winning a game twice. Okay? A compound event consists of 2 or more events. 2 events are independent events if the occurrence of one event does not affect the probability of the occurrence of the other. And we're going to see what that is trying to tell you in that statement. Okay, so the key concept. Probability of independent events. If A and B are independent events, then the probability of A then B is equal to the probability of A times the probability of B. So let me show you guys an example so that this key concept is more concrete for you. So take a look at this. Here's the example. Probability and independent events. You and a friend play a game twice. What is the probability you will win both games? We're assuming that the probability of winning is a half. Okay? And here's a big hint. Or here's a little review. What's the complement of the probability of winning? What's the complement of winning, the event winning? Do you guys remember? I heard it. Somebody said it. What's the complement? I heard it again. Somebody explain a little bit more. So can you tell me can you tell me how they worded that in the last lesson? Complement. You're right. It's the opposite. What's the opposite of winning? Losing. So the probability of a loss is a half, but another way we can say that is the probability of not a win. Okay, remember? Okay, I'm just trying to refresh your memory what the complement was. But who can tell me, if we know the probability of a win is a half, what's the probability of a win and then a win?
25 to 75.
Shh, I have a lot of people calling out. I prefer you raise your hand, please. Robert, go ahead.
25 to 75% chance.
No, I need you to give it to me as a fraction. I didn't say a percent or a decimal. Who can give it to me as a fraction? Nima, what do you got? What's your probability of a win and then a win? How'd you come up with 1/4? That's correct.
Since half of the win is half, multiply by half.
Very good. So that's exactly correct. So Nima said 1/4, and she said the probability of a win is a half, and we're going to multiply that by the probability of another win, which is also half. So that's 1/4. Okay? All right? Are we good? Now, what's the probability of a win and then a loss? Think about that. And then if you think you have the answer, raise your hand so I can call on you to share it with the class. Terrell. It's not a half. Chin. It's 1/4 again. And the reason why is because what's the probability of a loss? 1/2. So it's going to be a 1/4 again. Now, just to kind of get you guys to think about sample spaces, because we covered that recently. Okay, first game could be a win or a loss. Second game we could win or lose. So do you guys remember the sample space? Here, if I have W, L, W, L, I can have W, W, or a loss and then a W, a win and then a loss. That should be an L. And so this should make sense when you think about the sample space. So for a win-win, how many total outcomes are there? There's 4 here, right? But how many outcomes are there for a double win? Only 1. And then down here, what about a win and then a loss? It's got, the order matters. There's only 1 where there's a win and then a loss out of 4. So do you see why it's still 1/4? Okay? All right. So later in the lesson, they talk about other ways to think about it. I just wanted to get you guys to think about sample spaces and how it relates to this. Okay, now we're going to start talking about dependent events, and there's a little bit of a thinking difference here. Okay, suppose you play a game with cards numbered 1 through 5. Okay, so we got 5 cards, and they each have a number, and they don't repeat. So it's one of my cards has a 1, a 2, a 3, a 4, and then a 5. Okay, so we have the cards on a table. They're face down, and we shuffle them up. So at random, you're going to pick 2 cards. Okay, the first card, when you pick it, you don't put it back in the pile. Does that make sense? So let's think about this. When all 5 cards are on the table, how many possible outcomes are there?
5.
There's 5 of them, right? So I pick my first card, but I don't put it back. Now I got to pick my second card, but now how many possible outcomes are there?
4.
There's only 4. Do you guys see how the thinking is a little different? Because now there's only 4 left, so now my possible outcomes are out of 4, right? So we decreased by 1. So that's how things are a little different for dependent events, because what you did in the first step changes the probability of the second step. Do you guys understand? So now let's talk about calculating it. And if you look, here's the key concept. It's still the product. You're still multiplying it, just like we did earlier, where we multiplied the probability of the first times the probability of the second. But now we're talking about dependent events. So if an event B depends on event A, the probability of A and then B is the probability of A times the probability of B after A. So let's look at an example so we can understand what that means. Okay, so we have Scrabble tiles, and they're spelling out all my students' favorite subject. Now, here's what's happening. You don't get to see these tiles. You know that these are the letters that you have. They flip them over, and they shuffle them up. And then at random, the first tile you select is M. You don't put it back. Then the second tile you select, okay, we need to find the probability of selecting the second tile. So in the moment, we're just trying to figure out the probability of the second tile. And the probability of the second tile being a letter A after I picked a letter M. So I can already tell by what you guys are doing in the class that you're on the right track. So you're already taking the first steps. Okay? Go ahead and calculate this out. When you're done, put your pencils down. So, who can share with the class? What is the probability of picking an A after you already picked the M? Okay, we didn't put M back in. We didn't put a tile back. We picked out an M, and then we didn't replace it. But then we picked another tile at random. And what's the probability of that tile being an A? No, I mean Mason. Sorry. 1 what? 1/5. How'd you come up with 1/5?
Well, since you took away the M, there's 10 tiles left.
Okay, so you're correct about the possible outcomes that remain. There's only 10 of them left. So we start out with 11. You picked a tile, and now there's only 10 left for your second choice. So the denominator part you got perfect. What's the numerator part? We're supposed to pick what? What's the probability of picking A? What's the letter we're trying to figure out the probability of? A, right? So how many favorable outcomes do we have? 2. Okay, so what's our fraction? 2/10. And then what your final result was? 1/5. Okay, so I didn't want to skip that step because I want people to know how to make the fraction. Okay, so it's 2/10, but remember we don't like to have fractions in simplest. We don't like to have fractions unless they're in simplest form. So probability is the fraction always in simplest form. So Mason's correct. It's 1/5 to select A. I'm going to come back to this problem later when we calculate the compound event. This is just the dependent event we're calculating, picking an A after we picked our first tile. Okay, so the next problem, take a look at this, a little different. You select a T at random, a T tile at random from those above. Without replacing the T tile, you select a second tile. Find the probability of picking an S tile. Shh, quietly to yourselves. If you need to reread the question, go ahead and read the question. Alexis, go ahead. You think it's 1/10? How many guys agree with that? It is correct. It is 1/10. And the reason why it's 1/10 is because after we pick out a tile, how many tiles are left again? 10. But how many S's are there in the pile? There's only one, okay? So it's 1/10. All right, I'm going to come back to these two problems because here's what you did. You calculated the probability of the dependent event, okay? Now we're going to figure out how do we calculate the compound event. And let's go into compound events, okay? Probability and dependent events. Okay, so we're going to talk about this a little bit. You select a card from a bucket that contains 26 cards lettered A through Z. Okay, so let's just picture this. We've got a bucket. We've got 26 cards. Each of them have a different letter of the alphabet. Okay? So without replacing, you pick a card, and without replacing it into the bucket, you're going to pick a second card. Okay? Find the probability of choosing C, then M. So these are dependent events because you're going to pick one, you're not going to put it back, and then you're going to pick the second one. So now we're not just calculating the dependent event, we're calculating both. And we're trying to figure out what's the compound event probability. Okay, so I'm going to just walk you through it. First, you need to calculate the probability of the first event. Then we got to take and find the probability of the second event, which is a dependent event. Now, to find the probability of selecting them in that order is the compound event. And how do we find that probability? What are we doing with those two fractions? Very good. We're going to multiply. So can you guys go ahead and finish that up? And again, I feel like this isn't very difficult, but if you're not paying attention, it is. Okay, can somebody walk me through this? Who can tell me, you might not know the final answer, but who can tell me the probability of choosing a C? What's the probability of choosing C? No, I don't think I've heard from you today. What's the probability of us picking a C, a card with a C on it?
126.
Very good, 126. Now, that's the probability of the first event, but now we need to calculate the probability of the dependent event where we select an M without replacing our first card back. What's the probability of the second dependent event? Picking an M. Khadijah in the back? Very good, 1/25. Why did you say 1/25? So you can explain to the other students that may or may not have known. Right. So you don't replace the card. That means it changes the number of possible outcomes. So now there's only 25 cards left. Now, like you guys said earlier, in order to find the probability of the compound event, pick a C and then an M, you got to multiply the dependent event probabilities, 1/26 times 1/25. And then I'll just reveal that answer to you. That there it is. Okay, are we good? Because there's 26 cards. We haven't picked a card yet. So the probability of picking a C, if all the cards are in there, there's 26 in the bucket. But once I pick that C out, now there's only 25 in the bucket. Do you understand? And there's only one M in the bucket. So remember, it's 26 cards. Each of them have a letter. None of the letters repeat.
Okay, so I thought you already took the C.
The C, yeah, we drew the C out.
Shut up.
So we drew the card. Please be quiet. We drew the card that has a C on it. We already pulled that out. Okay? We're not going to put it back in the bucket, but we need to pick a next card.
Oh.
Okay, do you understand? That's why we got to subtract one from the denominator, because the number of possible outcomes it's less a card. Now, read this question very carefully, because the first period class tripped up on it. I'm going to go ahead and read it to you. It says, suppose another 26 cards lettered A through Z are put in the bucket. Okay, so how many of each letter do we have now? Two, okay, keep that in mind. After randomly selecting a card with the letter J, and without replacing the first card, find the probability of randomly selecting a second card with the letter J. So the problem is all different now. I need you guys on your own to work this out really quickly. Some of you guys were like ready to rumble. You knew exactly what to do. Some of you guys, try it. It's okay. You might get it right. If not, this is where we're going to fix it. Put your hands down for now. Some of you guys are ready to answer. I know I want to let everybody have a chance to try this. We're not ready to discuss this yet. Right now, you need to try this independently. Alexia, you might not have the answer. Can you walk me through the first steps? First of all, what's the probability of picking our first card to be a J? Now, you said 1 over 52, but remember we have two sets that we put in the bucket, right? Very good. So remember we have two J's in the bucket now, right? And there's a total of 52, so you got the possible outcomes correct, but you forgot there's two J's now. So there's 2 out of 52. That's correct. Now, what's the probability, if we don't put that first card back in that we drew, what's the probability, Alexia, of picking the next card to be a J? That's correct. So now that we've already pulled out a J, there's only one J left. So there's 1 out of 51 cards because there's only 51 cards that are possible outcomes. T, do you have a question? What's your question? Because we put in the bucket 26 more cards. So we already had 26 cards A through Z, but then we added another 26 cards A through Z. So altogether we have 52 cards. Okay? So there's 2 of each letter now. Does that make sense? And then for the first J, there's 2 J's in that bucket out of 52 cards, right? So the probability of picking a J in my first try is 2 out of 52. Okay? And then if we don't replace that first card in, now there's only 51 cards left. The probability of picking a J, there's only 1 J left in if the first one we picked out, 1 out of 51. So that is the result right here. Okay? We simplify our fraction. Now you could have simplified this probability of J to begin with. That would have made your calculation a little bit easier. But there's the answer. Any questions about this? So let's go back and let's calculate the compound events for the last slide over here. So here we just found out the probability of the independent or the dependent event picking an A after we picked an M. What's the probability, and I'll do this in another, what's the probability of A and then, oops, not A, it was M. What's the probability of picking M and then picking an A after M? A, then M, then A after M. What's that going to be? Then A after M. So we picked an M, right? And without replacing it, we have to pick an A. We already figured out the probability of picking an A after M, right?
Are you talking about picking an M after you took the M out or the M you took out?
We picked an M. That's the first, right? And then the second event is picking an A after M.
Okay, so the first M is talking about the letters you took out.
Right, yes.
Okay.
Okay, so what's the probability of that? Probability of picking an M. And we got to multiply that by the probability of A after M. Okay? So what's the probability of picking our M? Robert?
It's 2 11s.
2 11s because there's 2 M's out of 11. And we got to multiply that by, we already figured this out. What's the probability of picking an A after the M?
It's 2 10s.
1/5, right? Or 2/10, but 1/5. Okay, so what is that probability, that compound event's probability going to be? 2 55ths. Are we good? Okay, we good? Now, how about this? We're going back to those same tiles. What's the probability of picking the compound event, picking what is it, a T and then an S? So figure that out. What's the probability of picking a T and then an S? Work it out, and then we'll discuss it. And while you guys are working out, I'm going to go ahead and write this out. Probability of picking a T and then S after a T. Okay, that's going to equal the probability of T times the probability of S after T. Well, what's the probability of picking a T? How many T's are there?
2 over 11.
Right, so 2 over 11th, and then what's the probability of picking S after T? 1/10. And somebody said earlier that it was going to be the same. Is it going to be the same? No. It's going to be 2 over what? 2 over 110. And we like to simplify things, so what's that going to be? 1 over 55. And here's a little review from last week. Do you guys remember the spectrum of an impossibility and an absolute certainty? You guys remember that? So would you say these are lean more toward an absolute certainty or an impossibility? What is the fraction going to be close to if it's absolute certainty? If it's an impossibility, what's the probability? It's 0, right? If it's an absolute certainty, what's the fraction simplified to? 1. So are these fractions closer to 1 or are they closer to 0? So are they likely to happen?
No.
Okay. All right. So I just want to discuss the different methods. So you toss a coin 3 times. If we toss a coin 3 times, are those dependent or independent events? Independent, because how I flipped the coin the first time doesn't change the number of possible outcomes the second time I flip it. There's still just 2 possible outcomes, right? So here I'm just going to review with you what I said earlier. We know how to calculate the probability of events, compound events. Okay, we multiply the probability of the independent events. And then we also know that we can create a tree diagram or a sample space. So here, the probability of getting a coin and flipping it heads up 3 times in a row, 1/2 times 1/2 times 1/2 is 1/8. If we look that over here, here's my tree diagram, and we see that there's only one outcome out of 8, because we have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. So the probability is 1/8. Got it? Okay. Now we're to the end of my lesson. How do independent and dependent events differ? How are they different? Carlos, can you take a guess at it? It does have something to do. Gabby, can you help him out? Nice. I like how you worded that. So independent events, the probability of one event doesn't affect the probability of the other event. Dependent, it does. Like we saw that when we took a card and we didn't replace it, it changed the number of possible outcomes, so that changes the probability. Okay? So here's what the book gives us for the answer. 2 events are independent if the occurrence of one does not affect the probability of the other occurring. Okay? 2 events are dependent if the occurrence of one does not affect the probability of the other occurring. So that's basically what Gabby said. Very good. All right, so here's what I need you to do. Take a look at this. It's multiple choice. We're not going to actually calculate this out. 2 independent events, A and B, both have a probability of 1/3. They're independent events, and they both have a probability of 1/3. Which expression represents the compound event, the probability of A, then B? Which one is going to represent that compound event probability? I hear some of you guys. Which one do you think it is? Choice B, the second choice? Yes. And so what would this probability be then? Come on, we just did a warm-up on this. Okay. Shh. Quiet, please. Okay. Are the events independent or dependent? Take a look at the first event. You toss a nickel, then you toss a dime. Very good. Most of you unanimously said independent. They don't affect the other. Right? If I flip a nickel, it doesn't change how many sides the dime has. It doesn't change the possible outcomes. That probability remains the same. Now, what about this one? You select a card, then you select again without replacement. That's dependent because on the second card, there are a different number of possible outcomes. That is a dependent event.